Well, today we're going to talk about multivariable functions. Okay, let's go over a review. In elementary calculus, we learned about function in one variable. In elementary calculus, we introduced a function like y equals to f of x. Well, y equals to f of x. Here we can freely assign numbers values to x, and the value of y is changing based on x. Remember that x is called free variable, or it's called independent variable. Why is that? We can freely assign any number to x, and then our y value is changing based on x. For example, you have quadratic function y equals to x squared. You can freely assign anything that you like to x. X can be 1, x can be 2, it can be a half, it can be square root of 2, it can be negative, positive, and so on. So the domain of this function is all real numbers. Why is that? We can freely take any real number, plug that in for x, and calculate y. So the domain is equal to R, bolded R, or mathematically speaking, the domain is the set of, use curly bracket, the set of all x values such that x is a real number. Close the bracket. Well, okay, what about y? Y depends on x, okay? Y is showing us how the range of the function is changing. Depending on the values of x, we get specific values for y. If you remember the graph of this function, the graph behaves like this. The domain on x-axis, every real number is acceptable from negative to positive, negative infinity to positive infinity, but the range of the function is on positive side of y-axis. This is our range. So we can write down the range of this function as the set of all y values such that y is 0 or a positive real number. Again, your range depends on x values in your domain. Well, so what are we doing? We are taking values on x-axis and we map them to values in y-axis. By what? By using this function x squared. Function x squared. This function, this machine takes values on x-axis, makes some changes, square them, and gives you some numbers on y-axis. Very well. So I expect you to ask, what if you have two free variables? What if you have three free variables? Instead of having x as the free variable, we're going to make a function with two or more free variables and then try to analyze that function. Very well. So now we're going to talk about a function with two free variables. Definition. Of multi-variable function. So a multi-variable function is a function with multi-free variables. A function with multi-variable. We mean free variables is usually denoted by f of x, y, z, and you can add the rest of the variables. In this case, x, y, z, and the rest of the variables are free variables. For example, we're going to start by introducing a function in two free variables. Z equals to f of x, comma, y is a function in two free variables. What are the free variables? X and y are free because they are in parentheses, and z depends on x and y. You can freely assign values to x and y, but z, the third variable, depends on these two free variables. Dependent. Very well. Let's take a look at just one example that is very similar to what we saw before. Take a look at z equals to, for example, x squared, now plus y squared. Okay. Here you have two free variables, and this is the variable depending on these two variables. You can freely choose anything for x and y, and z depends on x and y. Sometimes they write it this way. They say, hey, f of x and y is equal to x squared plus y squared. There is no difference between z and f of x and y. Well, okay. Now I expect you to ask, then you are adding another variable to the free variables. What changes do we see in the domain of this new function? For a function in two free variables, we introduce the domain this way. We say that, hey, domain for d sub f is equal to, let's write this guy down as f, is equal to the set of all. You don't have one number. You have two numbers, one assigned to x, one assigned to y. It means that you have some points, ordered pairs, x, comma, y, such that with the condition that x and y, both of them are real numbers. X and y are real numbers. Okay, so the domain is part of the plane. What about the range? Okay, the range of a two variable function is going to be z values. Z values. So range or R sub f is equal to the collection of all real numbers, z values, such that z is equal to f of x and y. Z is a real number. The domain is part of the plane. Range is part of the line. That's the difference between the domain and range. This machine, this function, takes points in the plane, Cartesian plane, these points here. There are points ordered there. This machine, this algorithm, this function, whatever it is, it takes these points in the plane and map them z equals to f of x and y and map them to z-axis, the line, z-axis. Just part of the line. It might be here, it might be the whole line itself, negative infinity to positive infinity. It might include some part of the interval, closed interval, half closed interval, depending on the definition of your function. Very well. So let's take a look at some examples to feel more comfortable about functions in two variables. Then we're going to talk about functions in three variables, and then eventually we can easily extend the idea to function in multi-variables. So let's write this summary here. Function in one variable, y equals to f of x. The domain is a subset of R. The range is also a subset of R. But when it comes to function, z equals to f of x and y, we learned that the domain is a subset of the plane. The plane is denoted by R squared, and the range is going to be a subset of real line R. Okay, so give us some examples. In this question, what do we have? We have the following function. Evaluate f of x and y, which is defined as square root of x plus y plus 1 divided by x minus 1 at the point, what is the given point to us? 3 and 2. And also find the domain. Find the domain. Okay. So let us take a look at this function. How many free variables do we have? We have 1, 2, 3 variables. Three variables are x and y. Very well. So evaluating this function at 3 and 2, it means that your x is 3 and your y is 2. What are we going to do? Easily substitute 3 and 2 for x and y into the function. So f of 3 and 2 is equal to, on the numerator, I have square root. Down there, I have x minus 1. So x is 3, y is 2, plus 1, x is 3, minus 1. So I get square root of 6 divided by 2. So what does it tell me? It tells me when x is 3, y is 2, my z value is square root of 6 divided by 2. So what's the meaning of that? It means that point with first coordinate 3, second coordinate 2, and the third coordinate, square root of 6 divided by 2, is located on the graph of the function. Here we go. What else? It says find the domain. Very well. What do I have here? On the numerator, I have the square root function. Remember that. To find the square root domain, we have to take whatever is inside the square root and set it greater than equals to 0. So let us write this recall for you. Recall the domain of square root of whatever that quantity is. Inside you have the radicand. Is radicand greater than equal to 0? So whatever is inside the radical, we're going to take that and set it greater than equal to 0. Also note that you have something on the denominator. The denominator cannot be 0. For a rational function, the denominator cannot be 0. Okay, very well. So I have this information that I learned from algebra, from elementary calculus. I'm going to apply those knowledge that I learned before for multivariable calculus. So inside the radical, what do we have? We have x plus y plus 1, which we have to set it greater than equal to 0. Also, for the denominator, x minus 1 cannot be 0. So what is this? It gives me the domain of this function. So domain of f is equal to the set of all points x and y such that x plus y plus 1 is larger than or equal to 0. And at the same time, x cannot be 1. This is the domain. This is part of the plane. From what we learned in algebra, we can easily visualize this. Okay. Let's visualize this then. There we go. I'm going to graph the domain. So this guy says x plus y plus 1 is greater than equal to 0. From what we learned in algebra, this means that y must be greater than equals to negative x minus 1. So negative 1, and y is 0, x is negative 1. So here we go. And here we have equality, so we're going to have a line. It continues. And it's larger than or equal to 0. So it's going to include right-hand side of the plane. And also we have to exclude the line x equals to 1. There is line x equals to 1. This is the line, so we're going to use a dotted line here. This guy, part of the plane, is the domain of this function. This is your domain. This is how we visualize the domain of a two-dimensional function. Very well. Let's take a look at this. Function that we have, this function z is equal to, let's see. Here we have x plus y plus 1, and the whole thing is divided by x minus 1. Very well, this is the 3D visualization of this function in this space. Okay. Suppose you have x times ln of y squared minus x. And you want to evaluate this function at 3 and 2. And also find the domain of this function. Very well. So first of all, we want to evaluate what is the z value when x is 3, y is 2. So when x is 3 and y is 2, we're looking for finding the z value. Okay, we just easily plug those in. Our x is 3 and our y is 2. Here we go. 3 times ln of. So 4 minus 3. We have ln of 1, 3 times ln of 1. This guy is always 0, so 3 times 0 is going to be 0. This is our z value. What's the meaning of that? It means that the point with first coordinate 3, second coordinate 2, and third coordinate 0 is on the graph. Next, we're interested in finding the domain of this function. Very well. Remember that if you have ln of a quantity, whatever it is, to find the domain, that quantity must be always positive. This is what we learned from algebra, elementary calculus. Remember that the graph of ln is like this. So whenever the quantity that is given to us, we have to take that and set it greater than 0. But we can freely add anything that you like to your x. It doesn't matter. X is multiplied by ln function. So for the domain is equal to the set of all x and y's. We have two free variables. We need to include both of them in the domain such that y squared minus x is always positive. Okay, this is my domain. I found the domain. But how do I visualize the domain? How do I graph the domain in 2D part of the plane? Well, it's not that hard. We learned how to graph a y squared minus x greater than 0 before. So y squared minus x is positive. It means that y squared is always greater than x. Remember function y squared equals to x. Graph this and then shape the correct sign. So since you don't have any equality, you're going to use a dotted graph and you're going to shape the right-hand side because y squared is larger than x. This is the domain visualization of the domain of this function. Let's visualize this function. So this function is x times log or ln of y squared minus x. Okay, let's see. Down here, we don't have anything. Okay. I think it recognizes this. Let me use a different function. Okay, perfect. It's much better. So this is this function in 3D. We can change the restriction on x and y. Just expand this and see the changes. But this is our function in 3D. This is our surface in 3D. So as you saw, we're very interested in graphing a function